Hello, we are group number 7, and we're going to be showing you Faraday's crank tank. Our members consist of Alvaro Llanes, Nick Scarpato, Will Torok, John Paulston, and Joe Sorega. Our interactive will teach the effects of time-varying magnetic fields and its accompanying electromotive force. This will be reinforced by the applied science of Faraday's law of induction, which states that the magnitude of induced EMF is equal to the product of the number of linkages turns and the flux associated with the coil.
For the final product concept, the concept was going to be a competitive setup where two users spin cranks attached to magnets of varying strength inside of different sets of coils varying in coil number. The speed at which power is generated will be based off the combination of magnet strength, coil number, and rotational speed from the cranks due to user's input. The first person to reach the maximum positive voltage for a capacitor wins, and an electrical discharge will display between two nodes, as seen on the diagram. The product is assembled from non-conductive plastic panels enclosing a microcontroller that analyzes the analog input from variable coil packets and magnets and lighting LEDs and discharging a capacitor according to input. For the crucial functionalities of our design, the change in electricity generated from rotational speed of the crank, number of coils, and magnet strength are necessary to show the properties of Faraday's law. These crucial functionalities relate to our needs for the design to clearly teach scientific principles of electricity and how they relate to real-life scenarios, i.e. electrical generation, and for the design to operate differently through multiple inputs. For our prototype designing Creo, as you can see in the diagram here, our crucial functionalities targeted with the prototype were the number of coils and the magnet strength, as those were the only variables within our actual prototype. The digital version of the prototype was helpful because it was able to further analyze the optimal key functions of the design with the ease of variable manipulation from the digital design.
So with our prototype, we had two experiments we wanted to run with them. The first experiment consisted of changing the number of coils and measuring the current generation with these different number of coil configurations. The adjusted parameters in this case was the number of the coils. The experimental outputs would be electrical current generated, which was measured in amperes. The second experiment was similar to the first one, except in this case we changed the different magnets, which changed the magnet strengths. In this case, the adjusted parameters would be the strength of the magnets, and the experimental outputs would be the electrical currents, which was also measured in amperes.
For the experiment, we varied two parameters. The first parameter was the number of coils, which we varied from 1 to 50 full coil turns. The second parameter we varied was the magnetic strength, which we varied from 1.5 pounds max pull to 2.1 pounds max pull. In the first experiment, we kept magnet A constant and varied the number of coils. The output was in microamperes, which we read from the digital multimeter. The results support Faraday's law, where the number of coils has a direct effect on the electromotive force generated. As you can see, when the number of coils increased, the average microamperes generated increased. In the second experiment, we kept everything the same except we used magnet B, which has a greater max pull strength. The inputs were kept the same, varying from 1 to 50 coils, and the output was the same units before, which are microamperes. The results were consistent with the previous experiment and Faraday's law, where we should expect the average microamperes generated to increase with the number of coils. This last experiment compares the different strength magnets against each other to test the effect magnetic strength has on amps generated. When the number of coils are kept constant, magnet B always generated a larger electromotive force.
As seen by the data, the correlation between more coils and more power generated is clear, as well as stronger magnet, more power. This concluded the prototype was successful. This experiment also highlighted some necessary areas of improvement, such as proper rotation, securing the coils, and proper alignment of magnet to coil. Additionally, on our lessons learned, we had learned that we needed a multimeter versus the integrated chip. The integrated chip we bought, while it can take direct voltage, was not capable of analyzing that voltage. So we had to switch to a multimeter so we can get the correct measurement of the amps, as well as any other measurements we needed. We also discovered we had a plunger effect. as shown in the video. This occurs when the magnet is forced into the coils and it has nothing to do with the rotation of the coils. We are concerned that this could be affecting our experiment negatively, so we conducted a side experiment and discovered that the rotation and the plunger effect were relatively negligible, leading to just the rotation to be the good data. The other thing we learned was tolerancing. We need to tighten up the tolerancing to make this a successful product on the market.
So one other thing we learned from our prototype is that the shaft needs to be fully supported. As was mentioned, there was a plunging effect that we ran into, and to remove this effect, we would support the shaft completely so it doesn't move forward and back, but instead just rotates. The coil supports need to be correctly machined as well. As the number of coils increased, it became more difficult to hold the coils down as we ran our experiments. For this reason, we had to correctly machine these supports. And other than these two problems, the prototype was deemed successful, which in our case also deemed the proof of concept was also successful, because our two crucial functionalities were in fact proven with our prototype. And thank you for watching our video. Here is an experiment.
For our experiment, we're placing the magnet within the copper coils, and when I rotate this crank here, it will produce electricity.